Hi everybody. So the next section that we're going to look at is section 5.3 on the definite integral. And I think we talked about sort of indefinite integrals in the last chapter. And so now we're going to kind of get to basically the punchline of the course. And we'll see that basically after this section we'll be able to fairly easily figure out fairly easily use a relative term, figure out the areas underneath curves, or at least we'll be able to do them without doing Riemann sums. So let f of x be a function defined on a closed interval. We say that a number j is the definite integral of f over ab, and that j, right, the definite integral is the limit of the Riemann sum, right? So this is the Riemann sum. We took the limits of those in the last section. If the following condition is satisfied, given any number epsilon, so given any small number epsilon, but that's still greater than 0, there exists a corresponding number delta greater than 0, such that for every partition, and now partition is the way that you cut up the x-axis. So what this is saying, for no matter how you cut up the x-axis of AB, with the length of the partition being less than, or the maximum partition being less than delta, any choice and any choice of number in each subinterval, we basically have that the Riemann integral will be close to the definite integral, right? So basically what this means is that you can basically just use an integral to figure out the area, right? So don't worry too much about this definition. So that brings us to the definite integral, right? We did indefinite integrals where we didn't have numbers on the top and the bottom. These numbers are called limits or bounds of the integral. So basically what this is saying is it's saying you're doing the integral of this function between a and b, right? So basically what you're doing is you're taking the antiderivative and then evaluating the function at a and b. Now you might wonder when can you integrate and when can't you? That brings us to theorem 1 of this chapter, which is if a function f is continuous over an interval from a to b, and if the function has at most finitely many jump discontinuities, so in other words, you can have a finite number of jumps or sort of small gaps in the function, basically one point jumps. So you can't have a continuous interval where the function is disconnected. Then the definite integral exists. You can actually find the integral, and it's said to be integral over AB. So what that means basically is, your function could be continuous over the whole range A to B. That's one thing that could happen. But the worst case scenario is you want your function to be sort of have this jump discontinuity, where the function maybe goes like that. And then you could integrate over each region separately from A to B. Right? Now, most of the functions we'll be dealing with will be continuous like this one, but the first thing we want to do is kind of just get used to this notation, and that is, basically writing the Riemann sum as an integral. Let's say we want to express the following limits, limit as a definite integral, right? So we're taking this thing, we want to write it as an integral. So basically we have to figure out, well, what's the integrand, and then what are the limits of integration, right? And P is a partition between -1 and 0. So P is some partition. We're taking the x-axis and chopping it up into pieces. Maybe they're equal pieces like we did before in the last section. Maybe each partition is a little bit different there. But we're saying we're letting the largest partition go to 0, and that implies that all the other partitions are going to 0 as well. So we're, partitioning this finer and finer, adding more and more rectangles. Again, the rectangles don't necessarily have to have all the same width, but we keep adding more and more, and we let basically the length of each interval shrink to 0. So the question is, what function is this operating on? Well, here's the width. So this must be our function, right? So what function is that? Well, c sub k is the number we're plugging into the function to figure out the height. So the function is just 2x cubed, right? Which is that. So all you have to do for this sort of problem is basically just go from here to here. Just rewrite it as an integral so you can kind of see the connection between the Riemann sums and the integral. Right, so it's not that bad, right? They'll usually give you the interval, and then whatever this is, right, that becomes the integrand or the thing inside the integral. Now you might wonder, okay, well, how do we use this to compute areas? Well, we'll talk about that. You might already kind of have an idea. Let's say we want to express the following limit as a definite integral, right? So we're partitioning this from 1 to 4, so the limits on the integral are going to go from 1 to 4. What's the function? Well, here's the function, so it'd be 1 over x. Let's look at theorem 2 from your book. When f and g are integrable, right, in other words, if you can find the integral over the interval ab, the definite integral satisfies all the rules back in table 5.6. So table 5.6 were those rules for indefinite integrals, so all the rules for definite integrals are satisfied. Or I'm sorry, I guess we didn't talk about that. Well, we might have talked about some things, right? Couple things to point out here. Basically what this first theorem is saying is if you switch the limits of integration, if you switch a and b, that changes the sign of the integral. If you have the area from a to a of the function, that should be 0, which kind of makes sense, right? So let's say this is a, and that's a, right? So you're trying to find the area of that infinitely thin strip, that should be 0. If you have a constant times a function, you can pull that constant out front, so anything that doesn't have an x in it, you can pull out in front of the integral there, as long as it's being multiplied times the entire function. You can add and subtract functions inside the integral, so if you have the integral of two things added or subtracted, you can calculate the integral of each thing separately. You can basically think of this as saying that you've got the area from a to b, and then this is saying you've got the area from b to c, so you've got some function here. And it basically says that the area from a to b plus the area from b to c should be the same thing as the area from a to c, right? So you can sort of add areas. The min and max inequality says that if f has a maximum value of f and a minimum value of f on AB, then the area is somewhere in between there, right? Which kind of makes sense, right? So let's say this is a and this is b, and you've got your function in here going along like this, right? If this is the maximum height of the function, right? So you know this thing here is this area, and what this is saying is if you take the maximum height, if you look at this rectangle here, right? The area of this rectangle, the maximum height times b minus a, should be greater than the area in here. Also, if you take the minimum height and look at this rectangle, right? The area here should be less than the area here. If you think about that geometrically, is what that's saying. And then this basically says that if you have some function that's always greater than some other function, so let's say you've got some function f going like that, and you've got some function g that's always less than that, then the area inside g should be less than the area inside f, basically is what that's saying. So basically what we're calculating here is an area, right? I haven't really told you that yet, but that's kind of what you can think of it as. Right, so here's just some similar graphs to what I drew on the last page, just they're a little bit better pictures than I could draw by hand, right? So this is sort of an explanation of the constant rule. You're just taking the area and multiplying it by some constant. Right, this basically says if you have some function and you add another function, you're just adding the areas there. If you have the area from a to b and the area from b to c, that's the same as the area from a to c. Here's the minimax function right here. So the maximum value of the function here is given by that. So it's saying that this area here underneath the curve is between this area, right? It's less than that area and greater than that area. And again, if you have some function g that's always less than some function f of x, then the function g here, the area inside g should be less than the area inside f, which kind of makes sense. I'm not going to prove those or anything. But let's look at these rules to evaluate integrals. So let's say that you have two functions, right? You can integrate them, they're continuous or piecewise continuous over their domain. Now, again, you might wonder, well, how am I getting these areas? Well, I'm just saying that that's the area. So basically, I'm saying that the area between 1 and 9 of this function is -1, right? And again, we've kind of seen where areas can be negative before. This is saying that the area between 7 and 9 of the function is 5, and this is saying that the area between 7 and 9 of this different function h is 4. Okay, so we can use this information to figure out certain things. Like, let's say we want to figure out the areas here. Well, let's say I want to find integrate this of this function, right? Well, I can pull the -2 out front and then just multiply it times this. So this will be -2 times 1, right? That will just be +2, I guess, right? This is basically saying I'm adding the area from 7 to 9 of F to the area from 7 to 9 of H. So that would be the same thing as the area from 7 to 9 of F of X plus the area from 7 to 9 of H of X. I guess I should put my dx's in here. I'm just going to switch to a different color pen here if I can find that one that works. And then, well, what's the area of this, right? The area of this is 5. The area of this is 4, so it'd be 4 plus 5, or 9. Right? So this would be 2 times -1 minus 3, or sorry, 2 times 5 minus 3 times 4, right? So that would be, what, 3? So this one here, remember, if you flip the limits of integration, that changes the sign. So this would become -1, which equals 1, right? Remember, that was one of our rules there, right? So if you flip the order of the limits of integration, that changes the sign of the integral. Here, you want to find the area from 1 to 7. Well, we don't know that, right? We know the area from 1 to 9 and the area from 7 to 9 of that function, but what I could do is take the area from 1 to 9, which is -1, and I could subtract the area from 7 to 9, right? So that would give me -1 minus 5, which would give me -6. For F, I'm taking the area here. I got to switch the limits of integration here, right? So I guess that would be -4. And then I'm subtracting a -5 from that, right? So that would be a 1. So just to reiterate this on the next page, right? So the first one you get 2. Second one you just add the areas to get 9. For this, it'd just be 2 times 5 plus 3 times 4, which is -2. For this one, you have to flip the limits of integration, which will change the sign to a +1. For this, I'm taking the area from 1 to 7, or the area from 1 to 7 will be the area from 1 to 9 minus the area from 7 to 9, which will be -6. And for this, I got to flip the limits of integration. And so if I do that, I'll get 5 minus 4, which would be 1 there. Oh, I guess I can interchange. Sorry, I guess that'd be, yeah, I guess that is what I got, 1, right? Okay, so it turns out, and I kind of let this cat out of the bag already, but it turns out that if f is non-negative, so if it never goes below the x-axis, and you can integrate it, you can actually find the integral over a closed interval, then the area underneath the curve, so between the curve and the x-axis, is given by the integral. Right? Now we've kind of seen before that if you let f go below the x-axis, you'll get negative areas, so you can always sort of account for that by changing the sign there. Right? Right. So if you want to find the area from A to B underneath this curve, you could just integrate it. Now this is a straight line, so it's kind of silly to do it that way, right? You could just break this down into a rectangle and a triangle. Here the area of this region would be negative. And here the area of this region would be negative, and the area here would be positive. So if I want to find the area between A and B, since the negative region has a larger area, the area, in this case in air quotes, would actually be negative. Now if you wanted to find the actual area, like let's say you're trying to build something of this shape, you could find the area here, which would be negative, just make that part positive, and then take the area there and make that positive. So remember, the integral is just an area. So one thing you can do is you might not even need to use calculus to solve some problems, right? Like let's say you wanted to find the area for this function, right? So this will be similar to the one we just did, right? So this function is a straight line with negative slope. So it starts up here at 4 and then goes down like that. And we want to find the area between 1/2 and 3/2, right? Well, again, you could just break that up into a square and a triangle and figure out the area there, right? So the length here is going to be 1, and then what's the height going to be? That's going to be determined by this. So for the rectangle, right, that length will be 1, I guess the height will be determined by the function. So if I plug in -3/2 for x, I'll get what, -3 plus 4, so that'll also be 1. So the area of this will be 1. And then I'll take 1, and I'm starting up here at 1/2. What's the height at 1/2? So for the triangle. So for the triangle, this length is 1. If I stick 1/2 in for x there, I'll get -1. So this height is, the height of this point is 3, but the actual length there is 2. So I'll get 2 times 1 times 1/2. So the area of that is also 1. So the area there will just be 2. Now it turns out you can do the antiderivative. We'll see that in a minute, but there might be some problems that you could just do geometrically, right? I guess if you maybe to kind of let the cat out of the bag a little bit early, if you think about what's the antiderivative of this, right? This is what we did earlier, right? That'd be 2x squared plus 4x, and then we get a constant, but we're going to stick these numbers in, so you'll actually get that constant will disappear. And then basically it turns out what you do is you stick in 3/2 and 1/2 in for x, and that should also give you the same area, right? In fact, it might be easier to do this one geometrically, but let's plug in here and see what we get. So just reducing this, right, this will be -x squared over 2 plus 4x. Let's evaluate that at 1.5 and 1/2. So that'll be -3/2 squared over 2 plus 4 times 3/2 minus -1/2 squared over 2 plus 4 times 1/2. Right, so basically I'm just taking this number, sticking it in there, and subtracting what I get when I stick in the bottom number, right? So if I work that out, what will I get here? I'll get -9/4. That's going to be divided by half, so that'll be the same, or divided by 2, that'll be the same thing as multiplying by half. And then the 2's will cancel there, so I'll get 6. Here I'll get 1/4. -1/4 divided by 2, so that'll be multiplied by 1/2, and here I'll get a 2. So if I work that out, I'll get what? -9/8 plus 6, and then minus, what's that going to be? -1/8 plus 2. Yeah, so I'll get a -1/8, so I'll actually get a +1/8 for that. And if I distribute the negative, I'll get a -2. So let's see, if I work that out, do I get 2, right? I should, hopefully. So if I take -9/8 plus 1/8, that'll give me a -1 plus 6 minus 2, which gives me what? Oh, 3. Something's not right there. The area there, 2. I must have made some mistake in here. Oh, sorry, this should be divided by 2, not 4, right? So you want to increase the power by 1 and divide by the same thing here. Sorry, so then get rid of that, get rid of that, get rid of that. So that'll be just 9/4. It'll be 1/4. Let's see that worked better. So this will be 9/4. 1/4. What's that? So -9/4. So it'll be what? -2 plus 6 minus 2. And then something's wrong here. I should get 2, but so anyway, I'll have to take a look at that one again later. But like I said, you can see in some cases, right, just thinking about it geometrically might be easier. Like, for example, if you look at this one, you might wonder, well, what is the antiderivative of that? We haven't really talked about stuff like that. Well, again, you don't have to think of it that way, right? Think of this as the top half of a circle, radius 4, right? Because you could think of this as your y. So you've got y is equal to the square root of 16 minus x squared. If you square both sides, you get y squared is equal to 16 minus x squared. And then you're just trying to find the area from 0 to 4, right? Well, what's the area there, right? The area of a circle is just pi times the radius squared, but you're only looking at a fourth of the circle, so divide that by 2, right? That would give you pi times 4, right, or 12 something. Right? So don't forget, it's just an area, right? So if you can do it geometrically, or if you want to do it geometrically, you can. Now, some things will be a little bit more complicated. So here's what we got. So I guess, I did get, sorry, yeah. So I guess I did get 2 there, right? So -2 plus 6. I was thinking I was going to get 1, yeah. So it does give you the right answer if you integrate there. So that's what we got for that. And then for the second one, right, it'd be 12.56. Now there are some integral formulas, and this kind of goes back to what we did before. If you think about what is the antiderivative of x, right? Remember, we added 1 to the power, so that would be the antiderivative. And then like I did in that last example, you just plug in the limits. So plug in b for x and subtract what you get when you plug in the lower limit, right? If you have a constant, again, you can think of this just geometrically, right? I mean, if I've got some constant function, here's a and here's b, and I've got some constant function, right? What's the area going to be there? Well, it's just going to be the area of a rectangle. It's going to be the width times the height, right? I guess you could also think of it as this way. If you think of it as an integral, you could pull that constant out front. So that's going to be cx, and then just plug in a and b, right? So that'll give you c times b minus c times a, and then you could just factor the c out to get that, right? So however you want to think about it, right? Antiderivative of x squared would be x cubed over 3. Plug in the b, plug in the -3. So these are some very, very simple integrals, right? You can see some will be much more complicated. Like actually trying to do this one analytically with doing calculations and formulas might be difficult. But if you think, if you can recognize something geometrically, again, it's just an area. So let's use these equations we just looked at, these equations, to evaluate some integrals. Again, you could just think of this as an area if you want, right? I mean, suppose like, for example, this first one, right, that's just the line y equals x between 0 and 4. So it's just the area of a triangle, right, where this length is 4, that length is 4, so the area there would be, 4 times 4 divided by 2, so that'd be like 8. So hopefully we'll get 8 for the area here. So employing the first rule here, right, if I've got x, that'll just be, again, x squared over 2, and then I just evaluated it 4 and 0. So it'll give you 4 squared over 2 minus 0. Well, that's nice because that's just going to give you 16 over 2, which does give you 8, right? So you can see it does give you the right answer. Here's the one we just did. I guess we just did that one the long way. Back here. Maybe I'll do it again just because I kind of messed that up. Again, if you can take the integral of each thing separately. You can pull constants out. So that'll be basically minus 2x squared over 2 plus 4x, and then evaluate it at 1.5 and 0.5. Right? Because 3/2 is the same thing as 1.5. And then so just simplify that. That'll be negative x squared plus 4x, evaluated at 1.5 and 0.5. So stick the top limit in first. Right, so let me maybe just switch back to fractions here, right? So that'll be negative 3/2 squared plus 4 times 3/2 minus what I get when I stick in a half, right? So that'll be minus 1/2 squared plus 4 times a half. What do you get there, right? So you'll get minus 9/4 plus 2 times 3 minus minus 1/4 plus 2, right? And I think that should give you the same, it should give you the same answer that we got before, right? It should give you 2. For something like this, again, if you think about it, this is symmetric, so you could actually integrate from 0 to 1 and then just double the area. But let's do it here. And let's maybe draw a picture of this one, right? So here I've got the graph of 3x squared, which is going to look something like that, and I want to find the area between -1 and 1, right? So like I said, I could just find this area here and then just double it because they look the same. But let's actually work it out here. So if I take the antiderivative of that, I'll get 3x cubed over 3. And then I just want to evaluate that at 1 and -1. So the 3's will cancel there. So I'll just get x cubed evaluated at 1 and -1. And so if I do that, I'll get 1 cubed, and then remember it's minus whatever the other one is, so that'll be minus 1 cubed. So that'll be 1 plus 1, or 2, right? So the area underneath the curve there is 2. And so here's the same thing I just did, just sort of typed out here. But you can see you get the same answers. Right? So maybe this is a little bit more legible. Let's maybe do another example. Right? So for this one, again, since I'm adding things, I can just take the integral of each thing separately. Constants I can pull out front, so the 2 I can pull out front. I could have also pulled the 3 out front, but I guess I didn't. What's the antiderivative of x? Well, that'll be x squared over 2. What's the antiderivative of x squared? That'll be x cubed over 2. Plug in 1, plug in 0. You know, the nice thing about 0 is those two things are going to be 0, so it's just going to be 3 times a half, which is 3 halves, and then plus 2 times 1/3, right? So that'll give you 13 over 16 if you add those fractions together. So like I said, one thing you do have to be a little bit careful about here is if the you know, if the function dips below the x-axis, right, then the area here will be negative. So if all you really mean to do is calculate the integral, it'll give you a number that doesn't mean anything. But if you want to calculate the area here, right, you'd have to take the area here, make it positive, and then add it to the area there. So one last thing we want to look at here is something called the average value of the function. This is kind of what we did before. But you know, let's say that you have some function going like this, and you want to figure out what's the average height, right? Like let's say you took all these points and you moved them to, you know, the average would be kind of somewhere around here, right? Somewhere between that and that. And so basically you can kind of think of this as taking the function and taking this area here and kind of cramming it in here. And you're basically trying to figure out what height would you want it to be so that the area remains constant, right? So that the area is the same here as here, but you change it into a rectangle, right? So basically what you have here is this is your height, this is your width, and that's the area. So if you think about it, that's just the area. This is the width of your interval, right? If that's A and that's B, the width of the interval will be B minus A. So you're basically just using the formula that height equals the area divided by the width, right? So now in this case we can actually find the exact area, whereas before when we did this in the previous sections, right, we couldn't really do that. But so imagine you want to sort of take this circle and cram it into a rectangle that has the same area. What height would that rectangle have? The area in this case, you know, if you think about this, this is a circle of radius 2, and we got the top half, right? So the area of the circle, you don't even need calculus to do this one, right? You could use calculus to find the area, but that would be pi times 2 squared divided by 2. So that'll be, what, 2 pi for the area. And then what's the length of the interval? Well, that's 4. So take your area, which is 2 pi, and divide it by the width of the interval. That'll give you your average height, right? So you're taking 2 pi divided by the width, which is 4. That'll give you pi over 2. Let's say you wanted to compute the average of this function on this interval. Now this one's a little bit harder to visualize or figure out the area than this one, so we'll have to use calculus to figure out the area here. Well, what's the area, right? I know I kind of did it down here, but let me maybe do it up here. So I want to find the area between 0 and 3 of negative x squared over 2. So I can pull that negative out front. I feel like, in fact, I can pull out the negative 1/2 in front. And then take the antiderivative of x squared. Well, that's going to be negative 1/2. Antiderivative of that will be x cubed over 3, but I still have to evaluate that at 3 and 0. At this thing. So that will give me negative 1/2 times 3 cubed over 3 minus 0 cubed over 3. Well, 0 cubed minus 3 is just 0, so it's going to be negative 1/2 times, what, 27 over 3? So that'll give me, what, 27 over 6 for the area there. And then just divide that by the length of the interval, right? So I take 27 over 6 divided by 3. I guess this I could reduce to, what, 9 halves. So if I take negative 9 halves and divide by 3, right, that should give you negative 3 halves. All right, well that pretty much finishes up that section. So we're almost on the verge of probably the most important result in this class, Now again, you might already have some idea of where we're going here, but it turns out that basically the idea here is, if you want to find the area, instead of using the Riemann sum, right, you could just use an integral. That's the big thing that Newton and Leibniz sort of figured out. Right? So we'll take a look at that more in the next section.